In section 4.8, Newton's method is introduced, which is a method for calculating roots or zeros for a function. There are a couple of homework problems on Newton's method, but I am not going to test you on Newton's method. What I have actually for you is a quick little project that I want you to do on Newton's method in Excel, or we're actually going to use Google Sheets. That way you can turn it in to me by sharing it with me. But I want to explain Newton's method really quickly and show you how to do the project, which is only going to take a few minutes. It should give you a little bit of background behind how it works and how the formula works. That way you don't feel like you're just kind of randomly plugging things into a formula. But really the whole idea behind Newton's method is for using a derivative to help find a zero for a function. We could also use this to solve equations, because if we were to pull all of our terms onto one side of the equation would be set equal to 0. And then technically we could consider our new either left or right hand side to be the function, and we'd want to be finding the 0 for that function. So this is used to find roots or zeros or x-intercepts, depending on just what context we're working in. These are all technically the same thing. Of a function. And it's just a formula that uses the derivative. So it's an iterative process, and that means it's a formula, it's a function that we use over and over and over again until we're satisfied to the point where we think we're close enough to the intercept. We also have to have an initial guess, kind of an initial idea of where we think that that root or that 0, that x-intercept is going to be. So I want to just quickly go through the formula and why the formula works the way that it does. So let's say this is f of x, and I make an initial guess, and I have no idea, unless I have a really good graphing device, which we might not have technically, and I say it looks like maybe, just with some random information I have from algebra, that that's pretty close to where my x-intercept looks like it might be. Or it's possible that that's a nice whole number value. So that's an easy number to work with. It might be that the actual x-intercept here is some crazy number that I have no good way of estimating. So the closest nice value to work with is a. So what we're going to do is we are going to figure out what the tangent line is at a. And I'm going to draw that tangent line. And we know the tangent line And that's not a great tangent line, but that's okay. The tangent line involves finding the derivative, right? So if I know my function and I have an initial guess at where I think the intercept is going to be, I can create my tangent line. So to find the equation for my tangent line, I need the slope of the tangent line, which is f prime of a. And to find the equation of that line, we would say y minus f of a, that's the y coordinate there, equals f prime of a times x minus a. Now this is point slope form for setting up the equation of the line. The point here is a comma f of a, and then the slope there is f prime of a. What Newton's method says is the intercept is an even better estimate. If we find the intercept of that tangent line and follow that down to the function, that is an even better estimate for where the zero is on that function. And if you look at the picture, it actually is. It is a much better estimate. So we need to take this equation here that we just created and find the x-intercept. So the x-intercept is when y is equal to 0. So if we set y equal to 0 there and solve for the x, and let me write some things down here. So Newton's method says the x-intercept of this tangent line is a better estimate for the zero of the function. So we'll take that equation for the tangent line and find its x-intercept. And the way we find an x-intercept is we plug in y equals 0 and we solve for x. So if I take that exact equation and say the y equals 0 and leave everything else the same, and solve for the x, I will have negative f of a equals f prime of a times x minus a. So to solve this for x, I need to divide over that f prime of a. And that will leave me just with x minus a. And then I can add the a over. And we're left with x equals a minus f of a over f prime of a. That is the formula for Newton's method. So they change around the notation just a tiny bit. And we're going to do this process multiple times, and it's supposed to get us closer and closer and closer to our intercept every single time we do this. So this a value was our first guess for the x-intercept. And then this x value here is our next guess for the x-intercept. And if we do it again, it should get us even closer. So this is our first guess. And then this is now our second guess. And it is an iterative process, which means we're going to do this again. And this now becomes our new guess. So what we do is we call this x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So the new x is equal to the old x minus the function value at the old x divided by the derivative of our function value at the old x. And we got this formula just by solving our tangent line for its x-intercept. So if we did this again, we would take the x-intercept of our tangent line and we would follow it down to the function, and we would now draw a new tangent line at that spot and say that tangent line and wherever its x-intercept is, which is, and I made that a little bit too thick, so it's hard to see, wherever that new tangent line has an x-intercept is going to be an even better guess. So I might have to start changing some colors here. So this was our, we call this x sub 0 because that's our initial guess. And we follow that tangent line down to its x-intercept. That's x sub 1. And we see where it hits the graph. And that's our x sub 1. Now it doesn't matter whether we look at it on the x-axis or whether we look at it on the function. It's still the same x value. Now if we draw the tangent line there, and look at its x-intercept and follow it up to the function, that should be an even better guess for the x-intercept, and it is. It got even closer. That is x sub 3. That's now our third guess. If you draw the tangent line there, it's going to get us even closer. Every single time we do this, it's going to get us closer and closer and closer to our actual x-intercept on the graph. And every time we do this, we're just replacing this x with the x we just found. To get a new x, you just follow this formula with the previous x. So what I'm going to have you do for a little project, it's only going to take 5 or 10 minutes, is we're going to set up a table in Excel to do this for us. You could certainly work this out by hand. You're going to want to plug a lot of this into the calculator because the decimals can get really crazy. And what's going to be a really good indicator on whether we're getting close or not is the y values are going to get closer and closer and closer to 0 because what we're looking for are intercepts here. So we're really close to the intercept if the y value is 0. And that's one of the things that we have to calculate along the way is the function value, which is the y value. So we'll know if we're getting close if that function value gets really, really close to 0. I am going to do a really quick example here on paper just to show you how this works. So let's say we want to find an intercept for f of x equals x squared, and I might have to change this slightly. I want to make sure that it has intercepts, plus 12x minus 5. And I'm going to look at Desmos to help me estimate an initial guess, which I call x sub 0. So I'm going to switch over to Desmos really quick. And we've got x squared plus 12x minus 5. And this does have two x-intercepts, and they do not cross at nice whole numbers. But it looks like one of them is pretty close to 0. So I'm going to say my initial guess is going to be at x equals 0. It looks like it's just a little to the right of that. So hopefully if we do the Newton's method starting at 0, Newton's method will get us close to where that x-intercept is. And I'm not going to say what that is right now. I want to see if we can get it on our own. But my initial guess is going to be x equals 0. So one of the things we need in order to do Newton's method, we need to know what the derivative for this function is. That's the slope of our tangent line. And that one we could do very easily by hand. And that is 2x plus 12. And to keep all of our work nice and organized, we set up a table for this. We need to keep track of how many times we're doing this. Sometimes we're going to do it a specific number of times. And sometimes we're just going to do this until we get to within a certain distance of where that intercept is. So I'm just going to go through Newton's method 4 times. I need to know what my x value currently is, what my y value currently is. That's one of the things that we need to know for this formula. What my derivative is. So I'm going to say y prime of n. And then I'm going to use all that information to calculate my new x value. And the formula, I'm going to write it down here, because the way that I get my new x value is I take my current x value and subtract y sub n over y prime sub n, which are the values in the 3 previous columns. So your first column is the 0 iteration, because we're using x sub 0. It's our initial guess. We didn't do any iterations of Newton's method to get it. So we want to know the y value when x is 0. And you just use your regular function to get that. If I plug in 0 to my original function, I'm going to get -5. And then if I plug in 0 to my derivative function, I get 12. So the way that I have them written, this is also f of x, f prime of x. Now I want the x-intercept of the tangent line that I would have drawn at x equals 0. Now we don't need to draw the picture. We don't need to actually figure out what the equation for that tangent line is. We just need the x-intercept. So Newton's method cuts out all that middle work for us and just goes straight to that x-intercept equation. So to get that x-intercept, which is a new, better guess for the x-intercept of our f of x, what we need to do is take our x sub n, which is 0, and subtract our y sub n over our y prime of n. So that ends up as 5/12. And if you want to, you can go ahead and change it to a decimal. And most of these problems, and when you do this in Google Sheets, it is going to be as a decimal. So let me grab my calculator. And 5/12 is 0.4167. And we're going to repeat this process, and that 0.4167 is now our new guess that we repeat this whole process with. So now we need the functional value at 0.4167. Now I encourage you to actually use 5/12 instead of a rounded value. So I want to know what the functional value is at 5/12. So we square it and do 12 times it and then minus 5. And we're going to start getting some really weird decimals. It's a crazy fraction. I'm just going to go ahead and put the decimals. I get 0.1736. Now, these y values are really important because if we're looking for the x-intercept, the x-intercept is when y is 0. Now, my initial guess, I was all the way down at y equals -5. I did Newton's method once, and it got me all the way to y equals 0.1736. That's really close to y equals 0. So Newton's method just once got me really, really close to an x-intercept. Now, it's not perfect, it's not great, but it's a whole lot closer. Now, I also need to know what my derivative is at 0.4167. So your derivative formula is 2 times the x value plus 12. And for that one, I got 12.83 repeating. And I'm going to use those to draw a new tangent line. And all I want out of that tangent line is its x-intercept. And that's where Newton's method formula comes in. The x-intercept is the current x value, 0.4167, minus the y value, 0.1736, divided by the y prime value, 12.8333. And I've got 0.4032 if I round it to 4 decimal places. So that's where Newton's method is telling me to move for my new x-intercept. And I'm going to do this one more time. I said I was going to do 4, but I'm just going to do 2. Then I'm going to go over to Google Sheets. So I'm going to do this one more time with 0.4032. I need to know the y value at 0.4032. So I go to my function. I'm going to square it. And then multiply it by 12 and subtract 5. And I get scientific notation, it's so small. So I've got 9.7024 e to the -4. That means move the decimal point to the left 4 spaces. So 0.00097. Remember, we're trying to find an x-intercept, and that is when the y is 0. That is extremely close to 0. Now I need y prime at 0.4032. So I'm going to plug 0.4032 into my derivative function. So 2 times 0.4032 plus 12. And again, another steep slope. And the size of your slope does not matter. So don't let your y prime value fool you. You will tend to have a y prime get bigger and bigger and bigger. And that's just going to make this amount you're subtracting get smaller and smaller and smaller. As you get closer to your intercept, you do kind of want to stay right around that same spot. So most likely your y prime value will get larger and larger. So 0.4032 minus the y divided by the y prime. This value is going to be really tiny, so I'm not going to move much. You're going to have to go out pretty far in the decimals to see much difference. It is going to be 0.4031 if I just round it to 4. So really just doing this ends up being, since this is the n+1 column, this is the result from 3 iterations. So just 3 iterations of Newton's method, and we got an estimate for our x-intercept of 0.4031. I'm going to go back to Desmos and see what Desmos has to say for that x-intercept. So remember, we said 0.4031. Let's see. And we want a y of 0, and it says 0.403. Now Desmos is only going to display 3 decimals. So if we were to round it to 3 decimals, we'd have it exact. We actually, using 4 decimals in our calculator, have a even better estimate than Desmos has. So that is beautiful. And we didn't need necessarily a graphing calculator. We could have done all of that with just a little handheld 5-function calculator. And we didn't even need to see a picture of the graph to do that either. So now what we're going to do is we're going to try to make this table in Excel. And we don't have to fill in every single one of these cells in this table by hand. What we're going to do is we're just going to fill in a few of the cells. And then the nice thing about something like Microsoft Excel or Google Sheets is once you've identified a pattern, you can just copy that pattern and drag it down as far as you want, and it will fill in the pattern indefinitely. So that's what we're going to do. So I'm going to go now to Google Sheets, and I have a different example that we're going to look at. And what you are going to do is you are going to do one of these on your own for a project. So this is going to be a Newton's method example. And the one I'm actually going to try here is a cubic function. So I'm just going to keep this nice and labeled. And I would like you to set yours up exactly the same way. Make sure your name is on here somewhere. So for the function, unfortunately, it's really not worth all the trouble to do the pretty math type. So just use the crude buttons on your keyboard to do exponents and things like that. F of x is going to be, for the example, I'm going to do x cubed plus x squared plus 1. And again, if we were to go to Desmos, you would see that this function has an x-intercept pretty close to -2. Not exactly. But my initial guess, which we call x sub 0, is going to be -2. So I'm putting this all off to the side. I want to keep track of this. I also need my derivative. And you work that one out by hand. So this is f prime of x. I need to know what this is. And the derivative for x cubed plus x squared plus 1 is going to be 3x squared. Plus 2x. So pretty easy. I'm also here going to remind myself of what that Newton's method formula is. Newton's method says to get the next guess, x of n plus 1, we do our current guess, x of n, and then we subtract our current y value, y of n, divided by its derivative, y prime of n. So I just want that to remind me. So just some information that I'm going to need over here on the side. Now for the table, I need to keep track of how many iterations I'm doing. I need to know what the current x value is that I'm working with, what its y value is, whoops, what its derivative value is, and then with all of that, those are the three things I need to get my next and hopefully better guess for my x value. Now your n's start at 0 because this first x value we get to plug in all on our own. We don't do anything to get that one. And I'm actually going to center all of this stuff. I like that better. Now, the first few we need to calculate on our own. And then once we establish a pattern, we can just drag it down from there. So y of n, that is my functional value at -2. I need to plug -2 into x cubed plus x squared plus 1. So -2 cubed is -8. -2 squared is +4. So -8 plus 4 is -4, and then plus 1 more is -3. So my y value is -3. And then y prime of n. So I need -2 plugged into my derivative. So -2 squared we said is 4, times 3 is 12. And then -2 times 2 is -4. So 12 minus 4 is 8. And we actually, and we should be doing these. This first row really doesn't matter, but it definitely matters on the second row. So we should not be doing these by hand. What I want you to do is actually be doing these as a formula. That's what's going to help us to be able to drag it down. So what we're going to do here is we're going to say, and you're going to see we're going to get the same numbers. So when we just work these out on our own, you see we got -3 and we got 8. What we should be doing so that our spreadsheet can recognize the pattern and continue the pattern for us, we should say that this equals the x value cubed plus our x value squared plus 1, because that's what our function says to do. Cube your x value and then square your x value and add 1. And then this is where I have my x value stored. So so that's why I was referencing that particular cell, because that's where I have my x value stored. And notice we got the exact same answer. We got -3. And then when I do my y prime, again, I need to reference my x value, but I need to tell it the operations to do. So I have my derivative over here that says to do 3 times your x value squared. So I'm going to say equals 3 times my x value squared. And then we need to add 2 times the x value. And that's how we get our derivative. And again, we got 8. So perfect. Now to get our new and better estimate for our x-intercept, we need to use these values here. And I put my formula over here so I can remember. My new and better estimate is going to be my current x value minus, and I like parentheses. You never go wrong with some extra parentheses. My y value divided by derivative. And then close my parentheses, enter. That is my new estimate for my x-intercept. I'm going to go ahead and fill in my n values here. We want to go down to 9, and that will actually make our n plus 1 be 10. So that'll actually go through 10 iterations of our Newton's method. And then this x of n plus 1 turns into our new guess. Don't type it in there. We want to say this equals this value. We want it to reference the other cell. We want it to recognize as many other things on this spreadsheet as possible. We don't want to type anything in that we don't have to. We want it to recognize patterns. So again, to get the y value at this new value, we know how to get the y value. We cube it and square it and add 1. So we just have to use the new value is all. So this equals the x value cubed plus the x value squared plus 1. And don't worry about all the decimals. That's one nice thing about Excel or Google Sheets is you can leave all those decimals in there. You won't have to worry about rounding anything. For y prime, we've got a little bit different of a formula. We're going to say this cell is going to equal, well, our derivative is 3 times the x value squared. So 3 times my x value squared, and then plus 2 times my x value. So you're allowed to reference that same cell again. And because I have that same x value in my formula twice, I need to reference it twice. And then just hit enter. So that's the slope at x equals negative 1.625. And then I just want the x-intercept that the tangent line gives me. So again, I'm going to go back to my formula for x of n plus 1. And this is going to be my current x value minus the y divided by the y prime. Now, I like to do a second entire row. So my first row, this first row is not all formulas. This first row, I typed in the negative 2. Now, we did use a formula for these 3, but we did not use a formula for the negative 2. So we really only have one full row with formulas in it. Sometimes that's not enough for Excel or Google Sheets to recognize a pattern. So I like to do 2 full rows with formulas so it can recognize a pattern. So we do have one full row now with formulas. The n equals 1 row is all formulas. I'm going to do the n equals 2 row with all formulas as well. So this new x in the n equals 1 row is going to be my x, my starting x, in my n equals 2 row. I'm going to do it all over again. So I need my y value there. To get our y, we cube it and square it and add 1. So it equals this cubed plus this squared plus 1. And then I need also to know what my derivative is there. So my derivative is 3 times that value squared plus 2 times that x value. So equals 3 times that value squared plus 2 times that value. And then my new x value. So notice how my y's are getting smaller. That's good. That means we're getting close to our intercept. My new x value is my current x value minus, and I like extra parentheses, y divided by y prime. Now I've got 2 full rows of formulas. What you want to do is highlight it. And then see that little square in the corner there? We can drag it down. I'm going to drag it down until the bottom of where n equals 9, and it's going to fill it all in for me. And notice how my y's eventually just say 0, which is what we're looking for. Now, that's not always going to happen. It always depends on what x value you start with. And it's possible with some of these problems that you pick a bad initial x value and you can't find the x-intercept. So there are instances you have to pick a good starting x value, or Newton's method is not going to work. So this was a good starting x value. We were able to find an x-intercept. So our guess here for the x-intercept after 10 iterations of Newton's method is negative 1.465571232. So that's a lot of decimals. I could tell it to not show so many decimals. So we could, there's a way to format our numbers up here if you wanted to do that. You don't have to. Right here it says do decrease decimal places, increase decimal places. I could tell it, whoops, I didn't want to do that many. I get to tell it do 2, do 3, do 4, do 5, do 6. At some point, though, they're all just matching. And it will only display so many of them. So our guess for the 0 is negative 1.465571232. After 10 iterations of Newton's method, that's what we get. And I say 10 because we started at 0. And this last column says x of n plus 1. If n is 9, n plus 1 is 10. So really quickly, and I'm all done with my video, but really quickly, I'm going to go over to Desmos, and I'm going to type this function in, and I'm going to see if we have a 0 there. So in Desmos, x cubed plus x squared plus 1. Let me get rid of this one. And negative 1.466. So again, Desmos is only going to show 3 decimal places. They say negative 1.466. If we round ours to 3 decimals, it's going to be negative 1.466. So ours is actually more accurate than Desmos is. And I didn't use anything here. I didn't even use a graphing calculator to help me. So Newton's method is a really old method before graphing calculators, probably even before regular calculators were invented, for how people were able to figure these things out. So I am going to send each of you a function and an initial guess, and I would like you to create this same exact spreadsheet in Google Sheets. If you are in your email, you can click, and actually this is Google Drive. In your email, you've got these little blocks up here in the top corner that are your Google Apps. You can click on Sheets and open up a Google Sheet. If you've never done that before, just click on a blank Google Sheet and it will open up that exact page that I have here. And you can run through this whole thing that I just made. And then when you're done, it automatically saves. You can see right here it says all changes have been saved in Drive. What I would like you to do is click on Share. And when you share it, type my email address in there, which is SM, and when you start typing, I should pop up smlawrence923@nashcc.edu. So that will tell me that you are done and I can come in and grade it. And this is going to count as a project grade for this semester. So you've had one project already. This is going to be project number 2. Let me know if you have any questions. I'm going to email each of you a function and an initial guess to work with.